Today let us learn extrinsic semiconductor. The conductivity of an intrinsic semiconductor can be increased by adding suitable impurities to it. The process of adding suitable impurity to a pure semiconductor is known as doping. The impurities added are known as dopants, and the semiconductor obtained after adding impurity is called extrinsic semiconductor or doped semiconductor or simply impurity semiconductor. So we can say intrinsic semiconductor plus dopants gives extrinsic semiconductor. There are two types of dopants. First one is pentavalent. That is, the impurity atom has a valency 5, or we can say the atom has 5 valence electrons. For example, arsenic, antimony, phosphorus. They are group 15 elements. They have 5 valence electrons. The second group is trivalent. They are group 13 elements. Valency 3 or 3 valence electrons. For example, indium, boron, aluminium. When a pentavalent impurity is added to a pure semiconductor, we get N-type semiconductor. And when a trivalent impurity is added to a pure semiconductor, we get P-type semiconductor. So there are two types of extrinsic semiconductors, N-type and P-type. And the condition for doping is the size of the dopant atom and the semiconductor atom should be nearly same. Now let us see N-type semiconductor. In an N-type semiconductor, we are adding pentavalent impurity. For example, arsenic is added to a silicon crystal. The impurity atom replaces one of the silicon atom. So this is the impurity atom with a 5 valency. 4 of its valence electrons form covalent bonds with 4 neighboring silicon atoms. But the 5th electron is free. It is weakly bound to the atom, so at room temperature this electron is free and is available for conduction. Or this is the unbounded free electron, and it is donated by the pentavalent atom. So this pentavalent atom is called donor, as it donates one electron. And there are electron hole pairs generated thermally, generated by the breaking of covalent bonds. Electrons and holes are produced. So electron hole pairs, they are generated thermally, and the electrons produced by or donated by the donor atom. So we can say the number of electrons will be greater than the number of holes in an N-type semiconductor. Or the number of electrons, Ne, is very much greater than the number of holes. Or electrons are the majority carriers and holes are the minority carriers. And since electrons are negative charge and they are the majority carriers, the semiconductor is known as N-type semiconductor. And let us see the energy band diagram. And this is the valence band. In valence band there are electrons and holes. And conduction band contains free electrons. and the number of free electrons is greater. The electrons donated by the impurity atoms as well as the electrons produced by the bond breaking. So the number of electrons in the conduction band or the number of free electrons is very much greater than the number of holes in the valence band. And this is the energy level of the donor atom, or this is the energy of the fifth electron or the unbonded electron of the donor atom. It is very close to the conduction band, so that electron can easily move to the conduction band. So in this case, the majority carriers are electrons and minority carriers are holes. Now let us say the p-type semiconductor. In a p-type semiconductor, we are adding a trivalent impurity. And this impurity atom has only 3 valence electrons. 1, 2, 3. And these 3 electrons form covalent bonds with the 3 neighboring silicon atoms. But there is a vacancy in the 4th bond, or a hole is created in the 4th bond. And this hole is created by the trivalent atom. But this hole can accept electrons. So the holes can also participate in conduction. So there are holes created by trivalent atom, and as it can accept electrons, the impurity atom is known as acceptor atom. And there are holes generated thermally. Electron hole pairs are generated thermally. So the number of holes is greater than the number of electrons. Number of holes will be greater than the number of electrons. So we can say holes are the majority carriers and electrons are the minority carriers. And since holes have positive charge, the semiconductor is named as p-type semiconductor. And let's see the energy band diagram. In the valence band, there are holes created by the bond breaking as well as the holes created by the impurity atoms. But in the conduction band, there are electrons created by the bond breaking or electrons generated thermally. So a number of holes will be greater. And this is the energy level of the acceptor atom. The acceptor atom creates a vacancy, and so the holes are generated in the valence band. So the energy gap of a germanium crystal is, germanium atom is 0.72 electron volt, and only 0.01 electron volt is the gap between the acceptor atom and the valence band. Thank you.